Hi guys. In previous class, we had an introduction about current electricity. Current electricity is nothing but the study of motion of charges, and exclusively we are going to study much more about conductors. Conductors contains free electrons. To move to move these electrons, we required potential difference. And also we defined current we defined as the rate of flow of charge dq by dt. So charge units are coulombs, time units are seconds, coulomb second inverse, which also known as amperes. And one more important point, current is a scalar quantity. Even though we show the direction of current, suppose if you connect a circuit with a cell and a battery, with a cell and a bulb, suppose if it is an electric bulb, and if this is connected to a voltage source with a cell, and we can show the direction of current from positive to negative. So this shows about the direction of current. Even though we are showing the direction of current from which direction it is flowing, but still we will take that current is a scalar. So why? Because according to definition of scalar, it's a physical quantity which do not have direction, but current is having the direction. So still we will consider current as a scalar because it do not follow laws of vector addition. Or simply if you can take, it do not follow vectors laws. To define a vector, it's supposed to a physical quantity should have magnitude and direction. Along with that, it should follow certain laws. Then only we can consider that as a vector. But current still it is having magnitude and direction, but it is a scalar. Why? Because it do not follow vector laws. So that's the reason we will consider that current as a scalar. So today's class I would like to give introduction between current and voltage relation. So which in terms of Ohm's law. So Ohm's law says the current flowing through a conductor is directly proportional to the potential difference applied across it. The current flowing through a conductor is directly proportional to, I can use symbol at here, is directly proportional to potential difference applied across it. So here, whenever you can look about Ohm's law, be careful because Ohm's law only valid for conductors. So materials we classified conductors, insulators, semiconductors, like that, and this law is only valid for conductors. So we can better to write in the equation form, voltage is directly proportional to current, and we will remove proportionality symbol and we can replace with the constant R. So V equal to Ri or IR. So that implies we can define current I equal to V upon R. So here R proportionality constant, so that we call it as resistance. It's a resistance. So today we introduced a new character or a new property for conductors or insulators or any kind of that. So that new character is nothing but, or new property is nothing but resistance. So finally I can say about the Ohm's law. For a given conductor, the current flowing through a conductor is directly proportional to potential difference applied across it. So V is directly proportional to I and V equal to IR, and from that we can write the relation for the current I equal to V upon R, or if you can write anything of like that. And to find the property of resistance by using that, R equal to V by I. So voltage versus amperes. So we can divide these two, we can get a new character that we can call as ohm, and we can use symbol as omega. So resistance units are nothing but ohms. So if you can see this Ohm's law with the help of stimulation, which I am having it here. So this is a conductor. So this is a conductor. Here I am having controls. So I can control the voltage. So it means if you can see I can add a cell 0.9. So up to 1.5 I can add one cell. Suppose if you can take another 1.5. So like that I can increase the voltage. So when I increase the voltage, now you can see V equal to IR. Now the character current is increasing. The increasing here showing the size of the letter. So when we increase voltage for a given conductor, so when we increase the voltage, now earlier it is zero point 0.1 volt for the same conductor. Now you are increasing the voltage. So what happens? Through the conductor, current is increasing. So if this conductor having a resistance of 10 ohm, so it is having a resistance of 10 ohm, and if we can apply a 0.7 volt potential difference, so now we can calculate that as in terms of current I equal to V upon R. V equal to 0.7 volt upon 10. So if you can do that, that goes to 0.07 amperes. You can convert that as milli, so that goes to 70 milliamperes. So here in this simulation, the size of the letter indicates that the magnitude of increasing the value. Now if I increase voltage furthermore, you can see the current value is also increasing. So if we can remember, if 1.5 volt, if 1.5 volt is passing through 10 ohm resistance of conducting wire, so this wire is having only resistance 10 ohms. So by this case it is flowing huge amount of current, 150 milliamperes. And if we can increase resistance right at here, so the resistance will compensate, so it will balances. Now I am increasing resistance. Now here you can see the fall, the drop in current. When the resistance increases, the current value decreases. When the resistance decreases, the current value increases at a constant voltage. If the potential difference is constant, and current and resistance are inversely proportional. When the resistance decreases, current increases, and when the current increases, resistance decreases. That happens at a constant potential difference. So here the resistance is this conductor property, the material property. So even though if you take a very good conductor like silver, gold, copper, aluminum, still they are having resistance. So here we won't get till now a 100% pure conductor which having zero resistance. So zero resistance material zero resistance material till now do not exist. Still, there is certain resistance exists even if you can bring a best conductor, because the resistance now it becomes one of the cause and effect. So we will discuss about that, what is the cause for the resistance. So as a conclusion to Ohm's law, I can say voltage is directly proportional to current. If we can increase voltage, current is also increases. So we can remove that proportionality and we can replace with a constant is known as R, that is resistance. So now that resistance is the material property. So the conductor what you use at here. Okay, by seeing this circuit, I felt you may confuse with that this connecting wire and conducting wire. So even though this is a connecting wires, but we are talking about this is the conducting morely. So that is I want to highlight. Or otherwise you can consider like this. So the material what we have taken at here, so we are going to study about this conducting material, and here the black ones is only just supporting connecting wires from the potential source to as a conducting wire. So this is all about Ohm's law. So from Ohm's law we can define that voltage is directly proportional to current. So if you can draw a graphical representation for Ohm's law, since we will plot that Ohm's law versus voltage versus current curve. So by plotting that graph, always it gives proportionality. If you can take that as voltage versus current, so it gives a straight line. So the straight line which is passing through the origin, so that gives the voltage versus current. And if you can calculate the slope of this curve, slope is nothing but always y component upon x component. Suppose if you find the corresponding point slope at here and the corresponding point of the slope at the down, the slope of the curve which equal to r, which equal to v upon I. So slope you can find y intercept upon x intercept, or slope also you can find in terms of tan theta. So these are the two things we can find it out, that slope equal to y by x. So this is also we can find that y intercept upon the x intercept. So this is the concept of the Ohm's law, and Ohm's law gives about the relation between the voltage and current. Now we got a new character that's known as resistance. Now this resistance is a material property. So let us understand how this resistance affects the current. According to experimental evidence, we can say that resistance is directly proportional to length of the conductor what we have chosen, and resistance is inversely proportional to area of the conductor. Suppose this is the conducting material which I have taken at here. I want to find the resistance of this material. So the resistance of this material is depending upon the following factors. The factors which are affecting the resistance of this material, that is length of the conductor. The resistance is directly proportional to length of the conductor, and the resistance is inversely proportional to area of the conductor. Sorry, it's inversely proportional to. Resistance is inversely proportional to area of conductor. And if we can combine these together and write, so resistance is directly proportional to L upon A. So we will remove the proportionality constant, proportionality symbol, we will replace that with a constant, so that we can call as rho. So this we can call as rho, rho, rho times L upon A. So this formula is from the experimental evidence. So here rho is another character, so that's called resistivity. Resistivity. So I can say one more time at here, the resistance is a property that is existing for almost all kind of the materials, especially for the metals. We can say there is no metal which is having zero resistance. So we started to study from the experimental evidence. From the experimental evidence we can say that the resistance is directly proportional to length of the conductor, and the resistance is inversely proportional to area of the conductor. So together you can write resistance is directly proportional to L upon A. So resistance is equal to rho times L by A. So here rho we are calling as resistivity. So the resistivity is, we can define as resistance per unit area. How it is? So from this expression I can write that rho equal to, if you can rearrange resistance times area upon length. So resistance rho equal to, suppose if you can write area units, that is also meter square, and length units also in meter. So if you can cut one of the meters to one of the meters, you can end up resistivity rho equal to resistance per meter. So these are the dimensions. If you can take 1 meter of a conducting material with a resistance, so that is tells about how much it is having the resistivity. So now this resistivity is the another material property, just like resistance. So now this resistivity became the another material property. First let's see about the how this resistance changes with the length and area. Now here also same, the size of the character letter tells about the strength, how it is increasing. Suppose if see, they both are the proportional. It means if I increase the length, so what happens, the resistance value is also increases. Either we can concentrate at here the size of the letter, or here also having the numbers in terms of that. Suppose if we take 0.5 ohm centimeter resistivity material, that is, this is a resistivity material, a material which is having this much resistance. And now if you can play with that material length, if you can increase and decrease the length of the material, so the resistance also changes. So likely if we can increase or decrease area, now if we increasing area, the resistance value is decreases, and now if we decrease area, now if you can decrease the area, the resistance value increases. So because it is the inverse relation. Now finally I can say the resistance is a material property. The resistance factors only depends on length of the material and area of the cross section. For a particular material, if we take, different materials are having different resistance. If you can take copper, it is having different resistance or different resistivity, if we can say resistance in 1 centimeter area, sorry, resistance in 1 centimeter. Or if you can take deadly, very bad conductor which do not allow at all current, it is having high resistivity, just like wood or any kind of plastic. Now, the resistance only depends upon the length and area of cross sections. Why? Because in future we are going to see, just like capacitance having different size. Why the capacitance is having different sizes? Because of the area of the plates and the distance between them. Similarly, resistance also, we need to construct resistance of 1 ohm to several mega ohms. Suppose 1 ohm to 1 mega ohm. So mega means 10 power 6. 1 times 10 power 6 ohms. And this is just 1 ohm to 1 mega ohm. So the size of the resistance or the area of cross section of the resistor for these two different resistance is entirely different. So here also it is depends upon the physical factor, the length and the area of the cross sections. So finally here I can define that resistivity rho equal to, it is a resistance in a centimeter of the given material, that we define as resistivity. So the resistance is directly proportional to the length of the material, and resistance is inversely proportional to area of the cross sections. Together we can combine, and the resistance is equal to rho times L upon A. So here rho we define as new character or new parameter you can take for this conducting material. So that is resistance per centimeter. Now finally I define two things. One is resistance, and resistance affecting on which factors, and because of that factors we had to encounter with the resistivity. And resistivity is purely the material property. If you can change the material, the resistivity gets changes. Now if you can define that resistivity, the resistivity in terms of ohm meter or ohm centimeter. Now in next concept we will see how the resistance occurs, or what could be the exact reason for the resistance, how it will becomes into the existing in the nature.